Physical Science. We're going to continue on with section 2 here, talking about the gas laws. So again, we talked about how temperature, volume, and number of particles can all affect gas and the pressure of the gas. And now we're going to take a look at today several scientists who kind of worked on a way to mathematically kind of predict and figure out how each one of those will directly relate to one another. So there's going to be several equations with how gases are affected, again, all involving temperature, pressure, and volume. So our first law is going to be by a guy with the last name of Charles. So he's a French physicist named Jacques Charles. He collected data on the relationship between the temperature and volume of gases. The graph of the data showed a direct relationship between the volume of gas and the temperature of a gas. And here is what his graph looked like. So if each one here, so again, he plotted that at 0 degrees, the volume was around 7 milliliters, and then he just increased it more and more and more. And you can see as he increased the temperature, it caused an increase in volume, and so he noticed a direct relationship here. So what he did after he had all those points here, so he extended the graph beyond the measured data to find the temperature that would produce a volume of 0 liters. So again, at the increase of the temperature over there on the right, so again we're over at 100 degrees Celsius and the volume's almost up to around 9 liters, and so, or sorry, milliliters, and so he wanted to see how we would get it to 0. So what temperature would have to result into a 0 volume? And so again, he kind of extrapolated is the fancy word here, which means you kind of predict off your, again, he didn't actually have data to show this, so he just looked at the trend to see where it would fall. And again, so there's his straight line, and then if he extends his straight line, the temperature at the point or the line across the x-axis was negative 273.15 degrees Celsius. So that number should be a little familiar to us because that is absolute zero. So he kind of predicted that, again, the temperature where we'd get a 0 volume would be at the lowest attainable temperature that we have. So we'll go down to our next slide, explains a little bit more. So this temperature is equal to 0 degrees Kelvin on the Kelvin temperature scale, and we call that absolute zero. So I'd make sure I write this down. So again, what this guy did is he was just looking at the relationship between volume and temperature. So he noticed as you increase the temperature, it increased the volume. So he wanted to know, well, so therefore if I decrease the temperature, it's going to have to decrease the volume. So at what temperature will I finally get the volume down to 0 overall? And again, he got this to the negative 273.15 degrees Celsius, which is also known as 0 Kelvin or absolute zero. And so based off of this, he came up with what is called Charles' law, and it states that the volume of a gas is directly proportional to its temperature in kelvins if the pressure and the number of particles of the gas are constant. So I'd make sure I wrote down his little equation here. So volume is directly proportional to the temperature. So they're basically directly dependent on one another. If you change one, it's going to cause a change in the other. If you increase one, it increases the other. If you decrease one, therefore it's going to decrease the other. And so his little equation here, we have T1 or V1 over T1 equals V2 over T2. And so what T1 and V1 represent are the temperature and volume of a gas before a change occurs. And then T2 and V2 represent the temperature and volume after a change occurs. So we're going to do some samples with these in class, but I would just be familiar with the fact that Charles' law is this right here. And again, it shows that volume and temperature are directly related to one another. So that is what Charles kind of contributed to our knowledge about the gas laws. Now another guy by the name of Robert Boyle, he looked at the relationship between pressure and volume. So he was not looking at temperature and volume anymore. Now he's looking at pressure. So the graph shows an inverse relationship between the volume of a gas and the pressure. So that means when you increase one, the other is going to decrease, and again, and vice versa. So again, and this one is showing an inverse relationship. So if you notice, again, we have right here, our volume was 0.5, our pressure was 200. So now we are increasing our volume, so we make our volume 1, and notice now our pressure has gone down. So that's what it means, again, to be an inverse relationship. So these are things we learned at chapter 1, and they're kind of coming back into play now. So again, an inverse relationship kind of shows Again, when you increase one, so in this case, in this graph, we are increasing the volume, but as we increase the volume, our pressure is decreasing. And you can see here, in this little picture right here, little plunger that is kind of changing our pressure. So again, pressure goes down as volume goes up. And again, there's our little graph there. And so Boyle's law states that the volume of a gas is inversely proportional to its pressure if the temperature and number of particles are constant. So again, if we change volume, that's going to cause, again, the exact opposite to happen in pressure. So we increase volume, it decreases pressure. We decrease volume, it increases pressure. And again, that's if everything else remains constant. So I would make sure we write down what Boyle's law is here, that the pressure P1 and V1, so pressure 1 and volume of a gas before a change occurs, and then P2 and V2 represent the pressure and volume of a gas after a change occurs. And again, I know this might sound a little bit confusing now, but make sure you write this down, and again, we will go over some examples in class. And so when we brought the work of these two together, we have what's called the combined gas law, so this is really important. So the relationship described by Boyle and Charles can be described by a single law, so we can bring their work together. So the combined gas law describes the relationship among the temperature, volume, and pressure of a gas when the number of particles is constant. So I would definitely write down this right here, P1 V1 over T1, so the pressure and the volume over the temperature equals the pressure, the volume, and the temperature after a change occurs. So what that means is if we know all three over here and we know 2 over here, we can predict what this one will be. And again, we will do samples in class because I know it's kind of hard to show samples over the computer. But again, just be familiar that we have Boyle's law, we have Charles' law, they come together and they form the combined gas laws. And our example here is again, this is a weather balloon, and it's filled with hydrogen and helium, and it carries a package of weather instruments up into the atmosphere. So again, this is a real-life example of why we need to know the gas laws, because the gas laws will explain the behavior of the gas in this balloon. So this is just kind of putting a real-life face on why we need to know this. So that's it for section 2. Let me know if you have any questions.